Hello, everybody. Welcome back to the video. And in this one, we will try to explain the neural like model backpropagation algorithm. And this one is a kind of key of the neural like model. And the math is not hard, but it is a little bit tricky to understand. I spent quite some time on these notes, but I still feel it's a little bit messy, but I will try my best to explain well. And before we watch this video, I hope you already watched the video before this one. So you will have the preparation of the notation, neural model structure, optimization, chain rule, multiple variable chain rule, and so on. So the backpropagation algorithm will based on those videos. And in these loads, I will start from the top. And I repeat the neural model structure I used in the notation video. It's a simple three-layer model with a cost function at its end and x as input. This is a very simple, basic, plain neural model. And I also list the so-called forward calculation. Basically, suppose you got all the parameters of the neural model, which is weight and bias. Then you feed the neural model with the input numbers. How you get the output of the neural model, which is y hat. And also, in order to evaluate the performance of model, you will also get the loss or cost function of this neural model. This is the forward direction of the calculation of neural model. And then the key part will be if we don't know the parameter, we assume a set of parameter, and after we see the performance, how we're going to update the parameter. Then the stochastic gradient method kicked in. So we use the gradient to update the weight for each iteration of the calculation, and how to update this weight and other parameters, and how to get the gradient. That's the job of the so-called backpropagation method. And as we mentioned, the chain rule, especially the multivariate chain rule, is a key for this backpropagation method. And I assume you already watched my chain rule video and also the multivariable chain rule with Jacobi matrix video. So I will not repeat this video there, but I will list some key concept here. So basically, there are two dependency diagrams corresponding to this simple neural model in order to understand the backpropagation method. And this one I draw it in black one. That will be the main path. And in this one, the variable of the neural model, which is net input, neural output, and cost, will be listed in this dependency diagram. And also, one tricky part will be in order to update the weight and the bias, which actually is not a variable of the neural model, which is a parameter, and you have to change your idea. So it suddenly will still have to switch the thinking, and you have to create a new dependency diagram in which the parameter w and b become the variable. And this is the tricky part of this algorithm. And once you understand this part, it will be a little bit easier. So in these two dependency diagram, and you follow all the black path dependency diagram, you will got the partial derivative of the cost with respect to neuron output, neuron net input. You will get everything. You got all the gradient. But this gradient you cannot be used to update the parameter. So you have to think in this layer, for example, there are three net input. You will treat at this point the weight of the parameter of the net input, but the output of the not neuron become a parameter. So once you switch that idea, using the Jacobi matrix I introduced in last video, you can simply multiply the partial derivative of cost with respect to the net input with the Jacobi matrix between the net input and the weight matrix. You can get the gradient of the weight matrix. Then you get information for this one, so you can use it to update your weight matrix. The same thing happened to layer 2, also layer 1. So after one of these back update, you got all the partial derivative of everything for the variable a, w, and also for the parameter w and n. And you use the partial derivative of w and n to backfeed into the stochastic gradient method or other numerical method to update the parameters of the neural network model. And after a certain amount of iteration, you will achieve a good estimation of your results. The training of the model is finished. So this is how to understand how to backpropagate using the dependency diagram. And in this part, and there's a few key Jacobi matrix we introduced in last video. I'll repeat here. The Jacobi matrix between the partial derivative of the neuron output and the neuron net input is a matrix of the partial derivative of the active function, which is a diagonal matrix, which makes it very easy to calculate. And also, the Jacobi matrix between the net input and the neural output of the near before is actually the weight matrix, which also makes it easy to calculate also. And meanwhile, in the green dependency diagram, the key Jacobi matrix, which is the net input, the Jacobi matrix between net input and the weight, is actually the neuron output of last layers vector transpose, which is available once you go through the forward calculation. So the brilliant idea of this backpropagation is the key is you have to, once you got the partial derivative of the cost with respect to the net input, you have to treat the parameter as variable to get the gradient of the weight of the bears. Then you can use it to update the weight of bears using this simple equation. And in this part, I write everything what I just explained here in a formula form. So we can use this to get the formula for the so-called backpropagation method. So we start with the initial guess of all the parameters of W and B. Then we use this forward calculation to calculate all the neuron output and the net input for every layer in the cost function. So basically means you know everything now. So then you go back to the layer 3, which is the last layer. Last layer is special, and because the last layer's partial derivative cost with respect to the neural output is very easy to calculate because you design a cost function, and it's a very simple direct relationship between the neural output with this cost function. So basically, you can very easily got the partial derivative of the cost with respect to the last layer's neurons output. And once you got that, with the help of the Jacobian AN, you can easily, using this relationship, get the partial derivative of cost with the net input of the third layer. By doing this, we have the from here to here's partial derivative. Then we think about this relationship easily. In order to get the partial derivative cost with respect to the weight, we can easily use this relationship, basically just partial of cost with respect to the n of layer 3 transpose multiplied by the Jacobi matrix between the net input and the weight of layer 3. And we already know this part PCN3 from here. So we know everything here because we already got we know the J and W also. And similarly, we will do the similar calculation back to layer 2 and 1. I don't want to repeat all the equation because It will take a lot of time. It's very boring. Please take time to look at this thing. And after we went through all this equation, we find out one key thing. The most important partial derivative in order to get a gradient of the weight or the bias is the partial derivative of the net input of neuron to the cost. So that's the reason here in most textbook we define this PCN of transpose as S, called sensitivity factor, and we each layer have one. Because when I derive this, I actually define PCN as a row vector, so we have transpose as a column vector. And once we design this, we come back to here, so we will know you directly got PCN from this step, and you don't need to do anything fancy here. And once come to here, you want to get the PCN2, and you come here, you can see the PCN2 equal to this. You put all the equation to here, you find out your PCN2 actually is this number. Once you got here, your observation is your sensitivity, which is PCN2 transpose of layer 2, is equal to the diagonal matrix of active function of layer 2 and multiply the weight matrix of layer 3's transpose, multiply the sensitivity factor of layer 3. This relationship will hold backward for each layer until the first layer. So by doing this, we got the formula of the backpropagation, which is the sensitivity factor of the layer is equal to the activation function's diagonal matrix multiplied by the next layer's weight matrix transpose multiplied by the sensitivity factor of the next layer. So from this equation, you can see why it's called backpropagation. So you start from last layer's sensitivity factor, then you use this formula to go back to calculate all the sensitivity factor of each layer. Once you got the sensitivity factor of each layer, we already give you the equation to get the gradient of the cost with respect to the weight and the bias for each layer. Once you got that, you can got the gradient of the cost with respect to the parameter of this neural network model. Then you can easily put into a stochastic gradient method formula to update your parameter. This iteration will go and go until certain criteria is met. For example, then no improve anymore. All the cost is meet certain criteria. By doing certain amount of iteration, the backpropagation will update the parameter of the neural net model, and when the new data come, it will produce a better results for your application. So this pretty much is all the idea of backpropagation, and here I try to use a two way to explain it. One, I call it two dependency diagram understanding way, the way to understand it that way. I drew two dependency diagram to show you how the backpropagation is done, and then I list it in a formula way to derive the formula for backpropagation. I know this will be very hard to understand. My suggestion will be you can pause the video, look at the notes, have a better understanding. If you cannot understand and miss some information from the video before, please go back to watch the video before this one. So I hope you have a better understanding of this backpropagation approach. I think that this is the first important thing when you try to learn the artificial neural network model. Once you understand the backpropagation, I mean, most neural network model in the future is a architecture of this simple neural network model. And then once you know how this engine works, you will have a better feeling of other neural network model. And every time when a new structure, new architecture of neural network model come, it will be easier for you to understand. You will feel very comfortable to learn the new model and the new architecture. That's pretty much all of it. And my suggestion is if you cannot understand, just pause it, go through the whole notes. And just to have some fun of this video, because this backpropagation is very boring, and I already tried to update this nodes a few times. I think this, to me, is kind of clear, but I know still very tricky. So basically, just to have some fun, write a backpropagation poem and to just have fun. So it's starting from the oldest person in the family tree, which is basically this guy. Kid's sensitivity is a product of his activation matrix here, his dad's transpose weight matrix here, and his dad's sensitivity. That's it. Yeah. Dad's weight matrix updated by the product of learning stuff here, his own sensitivity here, and K's transposed output, this one. So this goes on and on. Okay, that's pretty much. Hope you have some better understanding and have a little bit of fun of this poem. And happy learning, and hope this will help you to learn more complex neural like model, which the basic one is a Lego brick of the architecture. Thanks a lot for your time, and hope to see you in the next video. Bye.